So while we await for other students to trickle in, any questions on any aspect of the class? The other thing is, some of you have started sort of talking to me about projects, but I really encourage the rest of you to do that. If my regular office hours do not work for you, then send me an email and we can always set up additional times. Mondays, Wednesdays, and Fridays generally are open for me. So, although I haven't scheduled the regular office hours during those days, but just write to me. I think you should start doing it this week. Quite important, so that my expectation is next week we would at least have a topic and a team kind of analyze. So, again, those of you have already contacted me, great, but most of you haven't. Let's see. Today's lecture is going to be on platforms, and I'm going to do hardware first and then software. And next week on Thursday, most likely, a couple of my students are going to do a lecture on half a lecture from them on how to write sensing-oriented apps on Android. So kind of some sensor device talking to a mobile phone, going all the way to a cloud. So kind of that's a very typical that embedded gateway cloud kind of architecture I mentioned. So they'll kind of walk you through that. Some of you may have done that kind of work, but many of you haven't. And then later in the quarter, we'll also have another lecture on kind of Android under the hood in the sense of how the OS itself is structured and all. But I wanted to get an application-oriented sort of a tutorial out of the way. So we'll do that. Another thing, I think this room gets very stuffy and all, so maybe we can leave the door open. I know it's going to be a little bit noisy, but perhaps put a trash can or something. So I wished we had a room with windows, but we don't. Okay. Thanks. Today, like I said, I'm going to go through some of the issues that come up on platform side of things. And again, I gave you some sense of some of the platformish kind of issues in that introductory lecture here. We're just going to dive a bit more into detail. This itself, this area, those of you who are a bit more hardware inclined, I think I have several sort of project ideas. I expect to have a list out by Thursday, which are more hardware oriented. So come and talk to me. Okay, so if you look at kind of a generic embedded platform, and here I'm really talking about stuff either at the edge or perhaps in some case at the gateways. So I had a sort of a version of this picture. Yeah.
Are you going to be covering in this lecture Brillo and Weave as well? I think Google released
No, but I was actually planning to have one of the student presentations around some of these. So Brillo, Weave, there is also something called all joints like all scene, which is kind of more of a Brillo is more of the OS. All joint is more about how IoT devices talk to each other. So I'm going to be spawning them out as student things. Part of the reason is a lot of them are right now, the information available is very sketchy in any case. So Brillo is partly still vaporware since Google hasn't released a whole lot of details. So we're going to bundle up some related technology and have a presentation on that, but not in this lecture. So from a hardware perspective, as I mentioned in one of the slides last time around, there's a whole bunch of options when it comes to implementing kind of the core of these platforms in terms of how you can do the processing. So general purpose microprocessors all the way down to ASICs, and I've shown only 4 options out there, but there are a whole bunch of them. Memories, kind of something which we don't pay a whole lot of attention to, we kind of take for granted. A couple of things to point out. Number one, what you encounter in embedded devices, the memory hierarchy looks rather different than what we see in general purpose computers. So in general purpose computers, we're kind of used to this. You may have a few layers of cache, some sort of a static memory that forms those caches, then a large amount of DRAMs, then some sort of a persistent storage, hard drive or flash drive. A lot of so firstly, embedded devices, for a variety of reasons, have deviated from the structure, even as you encounter currently. So, one way that they differ is the following: memory. It's very hard to make DRAMs on the same chip where you are making a processor, mostly because the semiconductor processes that are used, which are optimized for making DRAMs, are rather different from the ones which are optimized for making logic. So, uh, uh, so while there are some such things as embedded DRAMs, they're relatively recent and they're relatively rare. So when you find a microcontroller which has on-chip memory, it will usually be SRAM, and but SRAM is much sparser. Those of you are circuit oriented, it needs a lot more transistors per bit, much more power hungry. So it's costlier to kind of put in. So what you'll see typically, the structure would be in these embedded processors, which have onboard memory, that some amount of SRAM and then lots of flash. So you might see anywhere from a few kilobyte to maybe, if you're lucky, high-end a megabyte of SRAM. But that's really kind of the Cadillac of microcontrollers. Usually it would be tens of kilobytes. And then the flash would again be anywhere from hundreds of kilobytes to, let's say, a few megabytes. Now, of course, flash, the problem is while you can write to it, it's extremely expensive to write. And moreover, the write cycles that flash memory has is limited, so you can't really use it to store data structures that you'll repeatedly write. So now the story kind of changes once you move one level a little bit higher up the stack, and you start looking at things like BeagleBone Black or Raspberry Pi and all. There we do have DRAMs. They are obviously off board in that case. So usually a DIMM or two would be a couple of DRAM chips. So you start finding them, but of course it comes with the penalty of that. Now you're looking at sort of higher power systems which are not milliwatts, but perhaps order of a watt or so. Now, the way things have begun to change is that there is a lot of innovation happening on the memory side. So there are new types of memories emerging, and one big change which is begin to happen is that we are seeing memories which have DRAM-like speeds and densities, perhaps even, but flash-like persistence. So, in the sense that you power it off and it still kind of retains the data. So it's kind of squishing the memory stack in the sense that the separation of storage and sort of your main memory is sort of being revisited. And of course, flash itself, because of its advantages over kind of mechanical storage, magnetic storage, has also resulted in a lot of changes in these structures. So memory system itself, one of the big changes in recent years was the fact that it used to be that for DRAM to retain its memory, retain its contents, we have to refresh it, and that required burning a lot of energy. But around over the past 10 years, so we have seen these ultra low power mode in DRAMs where you can put them in sort of a low voltage mode, and then they can and still refresh them so they can maintain the content at relatively low cost, which is what made all these kind of devices where kind of you can shut your put the laptop to sleep for long duration, or your phones to sleep for long duration, and still they kind of wake up and immediately kind of the content comes up. So lots of interesting things happening in our sort of are still sort of going on. Power subsystem is another area where lots and lots of innovations which are happening. Part of it is simply the efficiencies involved. So for in each one of these, so roughly speaking, you'll have some sort of storage source of energy, a battery or an energy harvester of some form. Some sort of storage, the battery, and of course that's also the storage, but you also have things like capacitors and all. And then finally, some circuitry which cleans up voltage and all to supply this sort of thing. Each one of these things have the efficiency issues, availability issues. So again, lots of interesting sort of activities which are happening. Sensors and actuators, needless to say, but also the other area where lots of things have happened which are embedded specific or IoT specific are interfaces to the outside world. Radio protocols or new types of physical layers, as well as new ways of talking to the outside world, namely new kind of buses and stuff like that. So I'm going to touch upon some of these one by one. What are some of the issues that have come up? Again, some of the really current stuff, I will have some of the presentations on that, student presentations. Okay, so uh, um, um, when it comes to implementing kind of the core part of your edge device, very variety of options obviously there, and kind of the one which is easiest and for low end or low performance embedded system is you use some sort of a processor. Usually kind of the big players in the market, basically ARM kind of dominates, and Intel low-end devices are the one. But on the other extreme, the more common approach is to create some sort of a system on chip, either an ASIC type device in cases where performance or power requirements are really, really extreme, or very commonly done using FPGA. And the typical model out here is that there are companies that supply you so-called cores or intellectual property, IP cores is the term used, which are basically sort of implementations of useful modules in some hardware description language, Verilog or VHDL, and then you buy them, much like you buy software libraries. You kind of buy these cores and then put them on FPGA. Now, of course, there's a lot more value attached to these things. Oftentimes, these are given to you in obfuscated form, so like this is not easily understandable type hardware description language. They go through all sort of obfuscation on that, but there's a big market out there, and there's also a big open source hardware community. I had shown a couple of URLs last time around, which exist. Then, of course, the other tool in the arsenal is the ability to create custom boards where you use off-the-shelf components. So again, so we start out with easiest way, you buy a board which has embedded board, has some embedded controller. There's a whole market out there. Arduino, for example, or Mbed or BeagleBone are examples of that. Next one up, make chips. And then, of course, then you need to make a board around it. There's a rich industry around this. You can very rapidly prototype boards, get them made very cheaply. There are companies which basically you give them your whole design, and a few days later they acquire the parts and everything, they solder it, and you get the boards back. And for low-end stuff, it can be, if you're willing to wait a few weeks, small number of weeks, then the prices can be pretty low. If the quantities are high, prices can be pretty low. Let's see. So I already kind of talked about this, creating custom systems by just buying boards. There's a rich set of industry out there. And then finally, kind of using the board. So there's a whole bunch of these options that are out there. Again, kind of depends upon where, what the price performance requirements tend to be. Most commonly, what you see in educational setting and courses that you may have encountered are things around out here. That is, we either use some sort of a standard platform and then we can plug in things to it. Arduino and all these other platforms have some standard connectors, and there is a whole ecosystem of sensors and shields and things like that which plug into them, so you can create more industrially. There are kind of standard chassis, kind of backplanes with slots, and you buy boards to plug them into it. So if you're dealing with companies like National Instruments or things like that, they sell these kind of things. They are higher end, bigger, expensive, usually proprietary in some shape or form. To give you an example of kind of some of the kind of things that are out there, I mentioned previously FPGAs. So FPGAs give you the ability to implement digital logic, and many of them come with processor cores also on them. So they're chips with a processor and an FPGA, or more than one processor and a whole bunch of FPGA logic out there. Same kind of things also exist for analog stuff. So like, for example, a company called Cypress makes something called PSOC. And what PSOC is that besides the digital and the processor part, it also has an analog subsystem. So you can A to D converter, op amps, stuff like that. So you can create, for the low end stuff, you can create a complete system, including interfacing with the physical world. So all these options exist. You can buy devices which are just digital programmability, buy devices which have digital logic and processors, and you can buy stuff which have analog type things as well at various points in performance and all. Some of the FPGAs, the higher end FPGAs, can be really expensive. They can run into $10,000, $20,000 per chip. So obviously, the market for that is when you are making a few devices, because if you have a large volume, then you're better off creating an ASIC where you'll get better performance and lower per unit cost eventually. So this is so the whole bunch of these things are out there. I've shown this slide before, so I'm going to skip that. So the most common usage, and probably the vast majority of you as in your projects and all will encounter, are the so-called microcontrollers. So microcontrollers are nothing but a CPU core with usually on-chip memory, some sort of persistent memory, flash usually, even though I've written wrong, and some sort of read and write memory, usually an SRAM. In very rare cases, it might be some sort of a memory RAM. And then a whole bunch of peripherals. It's these peripherals which make microcontrollers distinct from standard microprocessors. So you will find things like, firstly, you'll find a whole bunch of more ports of the same type that you normally encounter, so Ethernet or serial ports and all. But then you'll also see a variety of ports which normally you don't encounter in high-end processors, like CAN bus. Anyone knows what CAN bus is? Perfect. What is it?
It's a control area. It's for control networks.
Yes, it's called control area network. Well, the main thing is it's found in cars. Okay, so on the driver's side of almost any car in the recent 20 years, there is this port called OBD2 port, which is a little connector with some 50 odd pins, which basically hooks up to the network in your car, and you can buy devices which plug into it. But basically, it's a CAN bus, at least in all American cars. So it's a slow speed serial bus. One of the things that car manufacturers are currently doing is they're switching to a much higher speed gigabit per second type network in the car. So CAN bus is few megabit per second, and I think the transition is now afoot to kind of higher rate bus. So, yeah.
What's that new bus going to be?
Pardon me?
Have they decided on a name for that new bus?
Yeah, the name slips me, but yeah, it's a standard procedure. Okay, so then you would usually find things which have to do with interacting with like motors and stuff like that. So PWM, pulse width modulation signals, which are used a lot, of course. And then of course you'll often find A to D converters or D2A converters built in, perhaps even an Ethernet, maybe sometimes even a radio on board. There are chips where kind of all of this, and there is a radio or also on board. So there's a rich industry out there which is basically catering to devices which just need to interact with the outside world. Usually the processors in these things are going to be somewhat lower end devices, so these are not going to be your sort of hyper-threaded, multi-core, those kind of things. They are sort of simpler processors, but there is a rich set of vendors which sort of provide these things. It used to be, sort of until reasonably recently, that most of these things were 8 or 16-bit. Okay, but in recent years, past let's say 5 years or so, the 32-bit market has emerged. So you can indeed kind of buy things where you can run lower end of a Linux stack entirely. These things can go up to a few hundred megahertz, and with external memory and all, you can get into kind of some reasonable sizes. But a lot of them are, particularly low power one, are really optimized for sort of low frequency ranges, milliwatt type power consumption, and that's where you see very low end memory structures and all. So when it comes to these kind of devices up here, namely 8, 16-bit memory constraint, or even 32-bit but memory constraint, you cannot get away with using Linux. Linux kernel itself, even if you were to highly optimize it and all, you'll probably still be in a couple of 100 kilobytes kind of footprint that, as memories go, is a huge budget for these devices. So there's a whole sort of suite of operating systems which are embedded OSs designed for these kind of devices. One other very crucial way in which these devices differ from what you would find in things which are able to run Linux and all is that usually there is no virtual memory in it. Okay, so those of you who have never done an architecture class, just a few sentences on virtual memory. So you have processor, you have physical memory, but in modern operating systems, for reasons of giving every process, every application an illusion of having its own memory, they basically provide an, kind of a virtual address space. And then a piece of hardware maps the addresses that are issued into an actual physical address through some sort of a translation table. Besides giving an illusion to every application as if it has its own memory space, independent address, it also provides benefits in terms of security and things like that. Okay, so these processors don't have that, and that has a huge implication in the sense, firstly, OS is simpler, but flip side is things like security and all. So we take it for granted that in Linux, my application cannot trash data structure of another application unless some explicit permission was given. You can, in these kind of devices, you cannot take it for granted. Everything is running in a single address space. Your stack, if overflows, it will trash something else. If you have a bug, your pointer goes awry, it will write somewhere else. So security, resilience, these kind of things which are taken care of by the OS are extremely hard to take care of in this one. So we'll see when I hit the software side of the story a bit, you'll see that things which are convenient to use in our standard computing are become problematic. So things like dynamic memory, things like sort of making sure that you're not going to trash each other. So a lot more emphasis on creating things which are correct somehow or the other. Okay, so a lot of emphasis in this world on perhaps someday being able to synthesize software which is correct by construction, as opposed to relying on human written software which then suffers from a lot of bugs. And also there's a more of a synthesis approach to software, much like we do it for hardware. So chips, again, you kind of give some sort of a specification, and EDA tools generate the hardware, and in the process make sure that things are correct and satisfy some properties. Same thing we see in the software at the certainly for these lower end devices, and increasingly for higher end stuff also. Yesterday there was a talk in EE where the faculty candidate talk, I don't know if any of you attended that or not, but the person was talking all about that how even little things like, let's say you're writing software for a self-driving car. Can you indeed guarantee that the braking system and the sensors will make sure that the car stops within a requisite distance, or that is, there is no bug to be able to do it? So being able to prove these kind of properties and all before you deploy is a significant challenge. So just because the repercussions of failure are a lot more significant. Okay, so microcontrollers. There are when it comes to big processors, we usually hear about companies like Intel. But when it comes to these tinier ones, there's a whole other set of companies, and there are a whole bunch more. But some of the popular microcontrollers, for example, there's a company called Atmel up in Berkeley who kind of makes very low power type things. TI, Texas Instruments, they are a big player in this thing. Some of the things you will see that they talk a lot about are extremely low power consumption. In particular, we'll see a bit later that it's also very important to have very low sleep power because these devices spend a lot of their time doing nothing. And if you're just burning energy, then that is drawing stuff. So optimizing for sleep mode is extremely important. Being able to wake up very rapidly from a sleep mode, that becomes very important. So a different set of considerations, and then having a rich set of peripherals. The one thing which I forgot to mention, you will find in peripherals is also timers and counters. In normal, when you're programming in Linux, if you want to do things like wait for a certain amount of time, things like that, then operating system gives you abstraction. So for example, if you want to wait for a few seconds, Linux offers you things like sleep and nano sleep and things like that. And likewise, if you want to wait for the time to hit a particular value, again, you make these OS calls. But the granularity or accuracy with which you can do those timing is pretty limited. In a lot of these applications, you may have to deal directly with timers and counters. You may want very precise nanosecond type timing or things like that. So, so usually these things provide sort of some rich set of stuff there. What you'll also see is that even the same manufacturer for the same cross microcontroller will probably offer you a whole bunch of different configurations because this is also an industry where pennies matter. Okay, so and things come at a cost. So if you need large amount of RAM, it's going to have implications on power and cost, silicon cost as well. If you want a different set of peripherals, then perhaps you should buy something different from the same family. So this just shows just from TI. From the MSP 430 family, kind of a rich set of options they offer in terms of RAM and flash and configurations of peripherals that exist. So usually the very first thing you'll face is just this challenge: what precisely do I need out of kind of the whole option of things out there? Whereas when it comes to, let's say, Intel x86 type microprocessors and all, there are some speed options and all, but sort of the choices are a lot more limited that are sort of offered.
Is that price per unit at 100 units?
These are probably large volume numbers, thousands or tens of thousands. Yeah, per unit prices are a lot higher. But at the low end, these 8-bit type stuffs and all, they cost fraction of a cent to make, not necessarily to buy. So. Okay, big player when you look at these devices besides so I mentioned Atmel and TI's two families, Atmel's AT series of devices and TI's MSP. The other big player in this thing is ARM. So the way ARM works is they don't make any chip themselves. So they design processor cores. They don't even design MCUs. They just design the processor cores. And then companies license from them, including Atmel and TI, but a whole bunch of others. And some of them are what are called as ARM architecture licensees. What that means is that they have licensed the ARM architecture, but they can make their own chip from scratch. There are very few companies who have the money to be able to do it. Apple, Qualcomm, Samsung, these are that model because they are making things in hundreds of millions of units. So they design things from scratch. Most of them go with the more standard option, that is, they buy the cores. ARM supplies them the core in the form of some obfuscated Verilog or something like that, and then these guys slap different kind of peripherals and all around it, and then sell that. And then they usually sell some sort of a board, possibly around it. So a whole bunch of companies. So besides Atmel, TI, you'll find a whole bunch of them. ST Microelectronics is one, but there are like many companies which are in the business of doing this. Freescale is another. A lot of companies in Asia are into that. Okay, I'm going to skip through this, just making the point that at the low end, you are dealing with memories and all which are significantly constrained and in kilobytes and kind of low megabytes. One thing that wanted to bring out was that a lot of these devices, besides speed and cost, a metric that we care a lot about is power. And power is a little bit of a tricky thing. And the example I have is from really old devices, but the point I'm trying to make is valid irrespective. So one thing to sort of keep in mind is that there are two different sets of considerations which come into play: power versus energy, and of course they are not the same. One is integral of the other. What you often may end up in a situation is that something which is low power may be so much slower because of architectural reasons that it consumes a lot more energy. And so this is some examples of a low-end 8-bit type processor and a 32-bit type ARM processor. And what you see out here is, and the y-axis is the energy and it's in log scale. So what you see out here is that the simpler processor versus this is lower power. In active mode, it will probably be, I don't know, 20 milliwatts because it was an older device. This guy is higher power in active mode, probably half a watt to a watt, so several order of magnitude more. But when you look in terms of energy, the story reverses quite dramatically. The left figure in each case is the low-end processor, the energy consumed by it to do a particular task. The right side is the high-end processor, whose power is higher, but it's so much faster that the energy consumed, the time dimension is a lot shorter, and the energy consumed is a lot less. Now, this holds true for things which are reasonable amount of computation. If on the other hand, you have to do something very simple like an interrupt comes, wake up, check something, go back to sleep, then the story would reverse, because the big processor, as kind of these lower plots tend to show, they take a lot of time to just wake up. And also, for example, if you're running on a 32-bit processor with a heavier weight OS and all, you might just spend milliseconds just waking up, setting everything up just to check the status of a pin. So that doesn't work very well. So for sort of this kind of quick and dirty, low amount of computation, these low-end processors have the advantage. So kind of this constant vigilance kind of activities. On the other hand, for bulk computation, you'll be better off paying the cost of waking up the processor. Sorry, you are on my sort of blind side, so I'm not seeing your hand raised up. Sorry.
Is that resumption time? Is that the OS resuming, or is that just?
It's a combination of things. Okay, so there are 3 or 4 different things which contribute to that wake up time. First is simply the getting the power supply and the clock up and running, assuming you have shut it off. Okay, there are multiple types of sleep modes. Some of them leave them running, but then your power consumption stays high. That number itself could be tens of microseconds, even bordering milliseconds. Okay. Then comes the cost of the OS. Now that is where the oldness of the slide shows, because the Linux numbers here are from really old version of Linux. Linux has improved significantly in its boot time. It used to be tens of milliseconds. Now with clever tricks and all, you are down to sub-millisecond type time frames if you have the right kind of devices and all. So these are 2 factors: clock and power, and kind of the OS boot up time itself. Okay, and the latter, obviously, a lot of optimization has gone on. And by the way, so for the former, and for the former, the other control you have is not to shut the clock and not to shut the power supply. So put them like just stop the processor, stop the hardware. It will stop consuming power, but your power supply will still. Clock, I would mention the clocks are using crystal oscillators and the surrounding circuitry, and just to keep them running can take you a milliwatt or so, depending upon. Okay, so if you really want to save power there, you have to shut them down also, and perhaps switch to some sort of a lower power, perhaps worse off type clock. Okay.
But in terms of hardware wake up time, just the time it takes to turn on the power supply and the clock, would that be comparable across the 2 devices?
Not necessarily, because the power system themselves can be quite different. So let me tell you why that can be the case. The higher end systems tend to have more stringent requirements on power supply, for example. So they may have regulators and stuff like that, whereas a lot of low end stuff oftentimes operates straight off the battery, no regulators, so nothing to wake up. So that itself could be the difference. And likewise, the type of clock you are using, again, if you are willing to deal with low performance, as in more jittery clocks and all, you can save on the power side and their wake ups might be easier. So the answer is trickier, but just to, I think currently, if you are doing these things, you're still looking into, let's say, certainly a few microsecond, perhaps even tens of microseconds in terms of wake up and all. And the reason power supply and all take this time is that they just have to charge up the capacitors and move charge around and all. And in case of clocks, the oscillator, the initial few oscillations are going to be very bad. I mean, if you look at when the clock starts up, the frequency is all over the map at the beginning. So one of the things actually you will find in some of the microcontrollers is the following. They will have an on-chip clock, which is made using what are called as ring of inverters. So it's basically an odd number of inverters sitting in a cycle, so that gives you a clock. But it's extremely bad clock because the delays of those inverters are not very tightly controlled. But your processor can start up and running. So some of these things, including some of the embed devices that I mentioned, what they usually do is they provide. So you start off in this mode where you have a very bad clock, but you can start executing the instructions, and that could be very rapid. And then, meanwhile, your main crystal is starting up, stabilizing, and then you set a timer, or the clock itself gives you an indication that it is now stable. And then you switch clocks so that from that point on you will have better timing characteristics. So for example, if you are doing some sort of a precise time measurement, those kind of things, then you will have to switch to kind of the regular the clock, but you start up with a bad clock. So you can do those kind of games. For power supply, unfortunately, you can't do anything like that, in the sense that you just have to wait for the power supply to kind of reach this thing. So back to the story. So anytime we face these options with different characteristics, time and again in computing, the option is use both and then switch back and forth between them, or do so in memories. The reason we have cache is precisely because we have these choices of memory. We can have fast, expensive, higher power SRAM, and cheap, dense, slower DRAM, and even cheaper disk storage, and so on and so forth. So what we do is we move the data back and forth between them. Okay, so we rely on the cache, a small amount of cache. Then if we fail there, we go to the main memory. Same thing with processors. You can have multiple processors at different points in this power performance space. They may have the same instruction set architecture, but just different implementations, or they may be just totally different. And kind of the idea is then you keep the little guy kind of responsive most of the time, and then when you truly need to, wake up the big person. And we in recent times, we have seen over the past 2-3 years, some of the mobile phone stuff have moved to that direction also. And at the level where you have identical instruction set, but processor cores at different points. And then you also see things like additional processors being there with a different instruction set architecture, which are doing things continually all the time. So like on Apple, on iPhones, Apple has this thing called M processor, which is motion processor. The motion processor is actually nothing but an ARM M4 processor, which they dedicate for handling sensory data. And if you look at Qualcomm Snapdragon, besides the main app processor, which you get to program, they also have some ARM cores sitting deep inside, which are acting as sensor processors. Okay, so this kind of heterogeneity we see quite a bit. The other type of processors that are very common in embedded devices are the signal processors, and mostly because a lot of physical world signals require cleaning up, filtering, some feature extraction, and things like that. And they rely on kind of what in E we refer to as digital signal processing. In a sense, they're optimized for sort of streaming numeric type tasks. And there are a whole bunch of companies which have historically specialized in this. What changed in recent times is that you begin to see these DSP processors being put on the same main processor as an additional core. So I mentioned Snapdragon. So all Qualcomm's chips also have a processor called Hexagon DSP. And in a couple of years ago, they opened it up. So if you're so inclined, you can always write an app where besides your main Android app, part of it can be running on that DSP that Qualcomm exposes. It's a totally different architecture. You have to use a different compiler and everything, but you benefit from the signal processing that it offers. In the same vein, we have seen sort of GPUs being used in the same way, which is that's an additional type of processor which exists on our desktop computing type devices for use in high performance computing. But for embedded side, there are a lot of chips out there where besides the main processor, there might be a DSP for the signal processing type stuff. That exists. TI, for example, some of the chips that TI makes for the embedded market have ARM processors, and then they have one of the TI DSPs on the same die, and you can split your computation between the two. That has also led to work in computer science side of things on programming environments where automatically kind of your application can be split between these two very different processors, optimizing for their power performance characteristics. Now, the goal behind a lot of these things, kind of having this mix of options, is what people refer to as energy proportionality. So, kind of the idea is that we would like our system to be such that the energy that it consumes is proportional to the work it has to do. So, in the sense that if I have to do very little work, that should be done with proportionately little energy, and if I have to do 10 times the work, then the ideal scenario would be that should consume 10 times energy. The problem is that most hardware is not like that. So high-end processors, they're great when so as I shown a few slides ago, they beat the little processors in terms of energy when we are doing lots of computation. The problem is all of that comes at a cost. We are using more transistors, we are using more complicated architectures to get all of that speed. And the penalty that we pay is that if we are doing little work, then also there is a high baseline. So if you think of the energy model, it might be something like a constant plus a term which is somehow increases with the workload. That constant term is very high if your design itself is more complicated. So hardware tends to be highly non-energy proportional if it is complicated. The little simpler ones have the advantage that their constant term is low, but then the slope the part which increases workload is high, so they kind of pay off the penalty there. So, so at the system level, what we like to have is energy proportionality. That is, if my system does little, it should consume little energy. If system does a lot of work, then we should accordingly sort of just ramp up. So this is an example of what might happen on a smartphone kind of situation where at different times we are doing different things, like when the user is swiping on the screen, there's a lot of events flowing around and all. When some game is being played, then perhaps on a periodic basis, some sort of screen update might be happening. In this particular case, there's a clock on the screen, and so every so often there's some activity happens to update the clock face, for example. So the whole this kind of mix of stuff which is happening, and in between nothing is happening. And what we would like is somehow a system which is very agile in the sense that when all this stuff is happening, its compute capacity goes up, and when we are doing nothing, it should switch back to kind of effectively act like a tiny head. So during this region, we would like it to act like a tiny low-end processor, and during the mode where we are doing a lot of activity, we would like it to act like a high-end processor, which is efficient at bulk tasks. And as I mentioned, that one of the things that has happened in recent times is that the processors on the mobile phones have this kind of heterogeneous architecture. They have multiple processors, some really low power processor taking care of continual background tasks, and then some processors which even for your regular application workload, a little ARM processor and a bigger ARM processor, and switching between the two. So Samsung's phones, basically, Samsung has this chip called Exynos, which they introduced a couple of years ago, which was the first one besides Apple's unknown devices, which was the first one to have this kind of a big little kind of mindset. Then Qualcomm Snapdragons also have that now. So you see this routinely, that otherwise identical in the sense of same instruction set from a programmer perspective, the same, but sort of two types of processors sitting on the same chip, and OS manages to switch back and forth between them. The dynamic range that you might see can be tremendous, and therefore lots of gains to be had by exploiting this. So the tools of the trade that we bring to bear are the following. First is, for the same processor, there are knobs that you have by which you can make it move between different points of power and performance. And the obvious one is we can change the clock speed. So if we lower the clock speed, the power goes down, we bump the clock speed up, but clock unfortunately results in pretty much a linear improvement in power and performance, so not very useful by itself. So what you usually will find is something called DVFS. Some of you were in my 202B, so you've seen this. DVFS refers to dynamic voltage frequency scaling, kind of the idea being, as we slow the processor down, we also lower the voltage so that all the transistors in effect slow down. That's one way of thinking about it. And it turns out as a result, we get a super linear improvement in energy. And so a big processor, we can get some degree of energy proportionality by just playing this game. Change voltage, change frequency, and you can do this thing on most of these devices. Obviously, there has to be support for changing the voltage itself. Okay, so the power supply has to be capable of doing it. And the next one is to put.
So when you do DVFS, does that mean just a lower power, or does that also usually mean lower energy?
Lower energy also. Okay. So the mantra, whatever, high level thing is the following. If you're willing to do things slowly, you're willing to do computation slowly, then you can do computation with asymptotically zero cost. I mean asymptotically with a lot of ifs and buts in that, but there's a trade-off between energy and speed. Okay. And in theory, in principle, you can do computation with zero energy if you're willing to wait longer and longer. Okay, so you can drive towards that. So I can play with a single processor. I can then have two processors of identical instruction set but different implementations. So it could be an ARM A series and an ARM M series. They have the same instruction set, so from perspective of compiler, effectively the same thing, but they offer you very different curves in this power energy space. Their higher frequency may be different. They just so the little guy may have a very different curve, and you kind of switch between these.
Yeah, is there a, from the standpoint of like layout and architecture, is there some kind of respect using DVFS as well, and doing that kind of implementation in your system? Because besides just the power perspective.
You can take any CMOS logic and make it work at different power frequency point. So that's not a problem. So being able to operate it that way is really an issue of having support for clocks and voltages that can be changed. One caveat, and which is what makes these things tricky, knowing what minimum voltage is needed for the hardware to operate at a particular frequency is not easy. okay, because it is a function of the specific device, as a function of temperature, as a function of a whole bunch of things. So usually these numbers, one way is that you sort of the manufacturer will give you some number and that is chosen to be conservative, because if you are wrong, if your voltage is too low, then you will have failures in the hardware, in the sense that your critical path would be longer than your clock period and errors will happen in that case. Okay, there are circuit techniques, and that's kind of getting to answering your question. There are circuit techniques which try to make this thing auto-adaptive, in the sense that I can just say, this is the speed I want, or this is the voltage I have, and then it automatically sets the other one accordingly. Okay, and then there are also techniques. A lot of work out of University of Michigan on what they do is they let errors happen, and so they try to be aggressive. You're going to operate the processor with as low a voltage as possible, let errors happen, and if errors happen on the rare occasions, at the hardware level, you have a correction mechanism for it. Okay, so there is kind of a circuit approach with approaches which kind of do that also. So there are sort of a mix. So I guess short answer to your question, a naive way of using DVF is you don't really need to do anything other than having clocks and power supplies which can do stuff, but there are sophisticated circuit techniques which make it a lot more efficient to do that. And then the final trick of the trade is to really have, yeah.
Sorry, when you said there's error correction being done on hardware, would that be off chip or on chip?
On chip.
Okay.
So actually what they do is the following. For every computation at the hardware level, there is actually a parallel computation which also kind of takes place conceptually. Imagine that the output of my combinational logic, I usually latch it into a flip-flop, right? Instead of latching it on the clock edge, I also have a second flip-flop where I latch it a little bit later. And kind of the idea is that the first one is wrong, I will fix it with the other one. Okay, I'm being very crude on it. I can point you to papers if you're interested in this, but these kind of techniques sort of. So final one is instead of this kind of a tightly coupled big.LITTLE architecture, you have a loosely coupled additional processor. This could be something which is domain specific, a DSP, a microcontroller, something which is super optimized for certain kind of tasks and sitting in the background and always running. And this is where the examples would be things like the M processor on the iPhones, or on some of the Qualcomm phones, they have something called a sensor hub, which is essentially a tiny little microcontroller which is just doing some additional stuff. So with all of these kind of, what ends up happening is that we essentially give the illusion of a hardware which, one other thing, of course, needless to say out here, and we shut down things which we don't need. Okay, so like for example, if my workload is less, then this guy, the little core will be up, the high core will be off. If I really am not doing any application level computation, then it would be just this background processor which is doing this stuff. So we kind of seamlessly under OS control move back and forth between these. So overall, the illusion we seek to give is that despite having these wide variations and kind of behind the scene activating, deactivating things, the illusion we will give is that our consumption energy that we consume is proportional to the work that we have to do in any given time. So that's the illusion we are going to give. So ARM, because its processors are so widely used in embedded, I think when they introduced this big.LITTLE a few years ago, that kind of caught on and started out with mobile phones, but you also see it in other kind of edge devices also. So for example, one of their first iteration had two of their A series processors. So they had the ARM A15 and an ARM A7. And just to give you a sense, A7 is what is called as an in-order non-symmetric processor with a pipeline of 8 to 10 stages. So in order refers to that every instruction is executed in the order it arrives. Those of you who have done any computer architecture class, it turns out that by doing things out of order and doing things like speculative processing and all, you can gain a lot more in performance. So architecturally, this is very simple. Single queue for all its execution units and blah, blah, blah. Simple architecture. A15 on the other hand, out of order processor, pipeline, which is a lot deeper. So it's optimized for higher performance computing, but all of that comes at a cost in the sense that so its gains show when you have lots of computation to do. So on a smartphone, A7 cores can do the easy stuff like sort of stuff which is computation not challenging, and A15 might get 10 when you have to do video gaming stuff like that. And it took a while before Linux, which sits under Android, was able to handle these kind of processing and all. But at this stage, it's all there. And as I mentioned, Samsung's Exynos was the first chip which had kind of brought this thing out. So it had 8 cores. 4 big, 4 little, and the way it would work is that there were constraints on it. If I recall right, initially, so there were 4 pairs. Each pair has a big and a little, and you cannot have both big and little be simultaneously on in a pair. So it has to be one or the other. So that's how kind of the thing was structured. And this migration itself, because if you shut the little, activate the big in a pair, all of that takes cost. So for example, the way this was organized was they had the same register set. So the 2 processors are sharing the same registers. They're identical in terms of instruction set architecture. To switch back and forth between the 2 involves a lot of things, like your interrupts may have to go to a different place. You'll have to worry about caches, things like that. So migration times of the order of 20,000 cycles, which is like 20 microseconds. So it's obviously not something you can keep doing all the time because there is a cost associated with it. You also, as I mentioned, you also have to migrate the interrupts, because if the interrupts were going to one processor and you have now shut it down, activated something else, the interrupt needs to go there. And also you have to invalidate the cache contents and restart that. So a lot of issues come up when you have this kind of architecture. And so besides simply saying, oh, I'm going to activate, deactivate, one has to take into account all these additional issues as well. So Linux, you have a question? No, okay. So Linux provides support for these big.LITTLE kind of things, which over the past couple of years. So significant sort of power savings by these kind of architectures. Some sort of a benchmark. But point is that using these kind of games, there are sort of very tangible application level impact which exists. Several projects had emerged when this technology had first sort of first came up, essentially enhancing the Linux kernel with support for these kind of big.LITTLE architectures. The other one is the more loosely coupled. So if you recall that picture, so I had the big little, and then I had this really little guy hanging off it. And this loosely coupled, heterogeneous, usually a processor which is not may not even be under the control of the same OS, may not even have the same instruction set. Usually, in many cases, not even exposed to the application. So lots of examples of those as well. In modern smartphones, and to some extent in a lot of higher-end embedded devices, you will find that you have access to a couple of different types of heterogeneous cores. Okay, and by the way, I said that also on other devices. The reason is the very same chips that we see being used in smartphones are now being pushed very heavily in other type of embedded devices. So like Qualcomm over the past 6-7 months is very aggressively pushing Snapdragon, which is their chip for smartphones, as the platform for the micro UAV, for the UAV industry. Okay, so that's a big push that they've been making. Same chip, just being kind of retargeted in a different application domain. And the point they make is the following. So Cray CPU is kind of the main app processor which Snapdragon has. They have GPUs, which can be used for a lot of signal processing, machine learning, those kind of tasks as well. And then finally, they have all these other specialized things. In particular, they have a whole bunch of DSPs, which I mentioned previously, so hexagon DSP, and some of which they have exposed. So on even on your Android smartphone, if it's a Snapdragon-based one, you can write code and download it to that DSP and use it for speeding up, let's say, some type of sensor processing and things like that. So you have these two different options. You have kind of the GPU kind of stuff, and then you have the hexagon DSP. Same story in a bunch of other platforms as well. I had mentioned Apple's SoC, same story. Now, Apple tends to be much less open about its architecture, but they do have this motion processor, which is similar to, as I mentioned earlier, at least in the initial generations, it was a ARM Cortex M4 type processor optimized just for sensor processing. More on the open side, TI's OMAP, which was before TI pulled out of the mobile sector, was used in many devices. Like Kindle used this OMAP quite a bit. I think they still do. So OMAP, for example, has a whole bunch of interesting processors. So firstly, it has big.LITTLE kind of a structure within the ARM processor family. So they have A15 cores, they have M4, which is the low-end ARM processor, and then they also have signal processors. So this is an example of a chip where there are multiple different kind of processors, again, targeted at the embedded market. Now, from a software perspective, kind of the interesting thing in this space has been that how can we hide all of this complexity from the application? If the application developer has to worry about all these different processors, what goes into big, little, loosely coupled, orchestrate all of that, that could be a pain. So for the big.LITTLE part, usually applications don't have to worry about it because the OS scheduling switches back and forth between them. So it activates the little processor or the big processor, as the case may be. When it comes to loosely coupled, like the hexagon DSP or in case of the TI chip, the M series processors, which cannot run Linux, then application has to get engaged. But there have been several projects in recent times, some work out of RISE, for example, where they manage that complexity for you, in the sense that you write as if you're writing on a single processor, and it takes care of compiling it for the both, moving things around, activating stuff.
Does the shadow kernel in the diagram just reference I guess, what is it?
Okay, yeah, so this one is specifically this work, K2 operating system, and what it does is that for every service on the big processor, on the main processor, on this heterogeneous other processor, there is a sister service or a shadow service that exists. Okay, and the idea is that if you need to shut the big processor, then there is an equivalent implementation of the same service available on the heterogeneous processor. The reason they are having to do this thing is the following: that now, once we are talking about heterogeneous, your instruction set architecture is different. You may not even have Linux on the other platform, but they still want to hide these things. So it could be like, for example, let's say a sensor sample coming in, you need to process it. Let's say you need to filter it. Okay, you can run the filter on either side. What they do is they take care of running that. Now, the shadowed services are specifically referring to, in their case, some operating system services where they have counterparts on both sides. So on the main kernel as well as on kind of the little other secondary processor.
So it's kind of like a backup, per se, maybe.
It's you can think of it as a backup, but it's basically kind of two implementations of the same service, one on the big processor, one on that one.
Or is this all like adopted by Linux? Or
No, so the little guy is not even running Linux, and in this particular case, they actually, for the whole thing, they had a different OS. Okay, but these M4 type devices, like these, are not even capable of running Linux. They don't have virtual memory, stuff like that, so you can't do that. Whereas, going back, like Exynos type stuff where you have Cortex A7 and Cortex A15, both are capable of running Linux. They are okay. It's just two implementations of processor, but both capable otherwise. Okay, whereas in this OMAP type stuff, or for that matter here, right? If you're parceling computation onto the DSP, it's a very weird, different kind of device, no operating system. So what such as K2 is trying to do is to really kind of create a OS which spans these very heterogeneous processors, basically. But this is more researchy, and this is one of the very few groups which have sort of done stuff towards that. So this it's not like something which is widely used. Okay, let's take a 5-minute break, and because a logical transition point, I'm going to talk about communication and I/O interfaces next. So 5 minutes, then we restart. Hey.
You said both the boards run Linux OS simultaneously, right? In the last slide.
Say it again.
You said these both run OS simultaneously.
It's actually a new OS they have created, and this new OS has the property that it has equivalent services on both sides.
So it's the same. I mean, it's the same kernel running on both.
No, because it's a very different processor on the other side. So no, it's not the same kernel. But so you can think of it as they have implemented their OS consists of a kernel running on this guy and a kernel running on the main processor, and they provide similar services.
So in this case, both the cores have to be powered on all the time. So isn't it back? I mean, towards the back side. I mean, we are not saving any power here.
Oh no. So they can certainly shut things off. So I mean, it could be that times just this little guy is up, not the big guy. So they power manage on top.
In one of the earlier slides, you wrote some peripherals called brown motion detection. In the earlier slides, like the third or fourth slide.
Oh, way earlier.
The brownout detection.
Okay, yeah, brownout detection refers to that when the battery voltage has fallen too low. So one of the things I had mentioned was that oftentimes low-end stuff is run without a voltage regulator. Okay, but then the problem is that as the battery voltage falls off, you have a problem, and if you continue to operate where the voltage has reached a dangerous region, then bad things can happen. So brownout detection is basically an early indicator of that, so that then the OS can start.
Excuse me, Professor?
Yeah.
Yeah, two quick questions. First one is, when is the office hour?
One day it is 1 to 2, the other day is 2 to 3. I think today is 2 to 3.
Today is 2 to 3?
Yeah.
Okay, and Monday is 1 to 2?
No, it's Tuesday and Thursday.
Tuesday, okay.
But if you want to meet me on Monday or Wednesday or Friday, then just write to me. And
Okay, I mean, I asked this because Ram asked me to ask you this, because he wants you to sign
okay,
this
yeah,
online form.
yeah. If you can, has he given you the form or something? Or
No, he just asked me the time.
Yeah, I need to reply to him. So thanks for reminding. But yeah, I'll do that. Yeah.
And second thing is for my PCB design, I think it's pretty much finished.
Okay.
Yeah, I asked the call. They give me some more feedback suggestions. I'm gonna modify that. I think I can finish it like before Thursday or Friday. So
Okay.
I just wanna kind of schedule appointment with you ahead so that I can.
I mean, we can meet today or we can meet on Thursday. If you want. Thursday is perhaps a little bit less crowded, or Friday if you're open. Friday is much better.
What time is Friday? Between 11 and 2. Okay, in your office? Okay, great.
So write to me a more precise time, and so that I can make it. Okay. Yeah.
You know what I mean? When you just straight up apply it.
Yeah, right.
Also, do you want to go to Europe? Yeah, so apparently what's happening is that they just opened a huge cell in Europe, and then they realized that, oh, since Europe is so fluid, a lot of people actually
Okay, let's restart. We looked through some of the issues surrounding the computing part, and firstly, if any of you are interested in exploring some of the newer things which are happening from the computing perspective, I think possibilities of projects out there, including, I think, if you have some prior experience with FPGAs kind of design and all, then one of the interesting things which has happened is that after getting sick and tired of university researchers not having access to any processor which is open, Berkeley a couple of years ago created something called RISC-V, which is an open source RISC core, and then a lot of people have picked up on that. So now we are seeing the emergence of completely open and very high quality embedded processors around that, including sort of peripherals and things like that. A group in Italy and ETH Zurich in Switzerland has then taken Berkeley RISC-V and created a complete embedded processor with some set of peripherals and all around it, which works on a widely used FPGA board called Z board. So I have a couple of project ideas around that, potentially in the sense of adding additional capabilities to that or exploring things in software around that. So if anyone is interested, that could be a project area to look at. Then additionally, there are things around operating system, particularly real-time and timing type capabilities on Linux running on these kind of platforms, as well as potentially adding real-time type capabilities on some of the newer languages that are emerging. So if you have sort of some interest or comfort with low-level systems programming, there are possible project ideas there. So switching to the next part of the embedded platform, namely its ability to communicate and interact with the outside world. So this one I'm going to do a little bit more shallowly, and then I'll have a lecture where I'm going to go into probably to one of them in more detail, namely Bluetooth LE, simply because it's being used very widely for working with sensors. But there's a diversified set of interfaces that you find. Many of them are coming from the general purpose world, and this is a constantly evolving list. But certain things like CAN bus, I2C, SPI, there are good old serial port. These are very commonly used in the embedded world also. And then there are a whole bunch of other very more specialized things. For communication, wireless is extremely common in many cases, including even in, we're beginning to see it in places where you could use wires, but the cost and lack of reliability with wiring often makes wireless a preferred candidate. And more importantly, the weight it adds. Okay, so a modern car or an aircraft with wires running all around and all adds significantly to both lack of efficiency to the weight and as well as reliability. So wireless also has been a big thing. But to give you an example, CAN bus, it's very old. It dates back to 80s or early 90s, I think, but it's still used in our cars. And it's part of the reason it still gets used is that it's extremely robust. It's designed as a serial bus, so twisted pair wires. And the way, I guess, I think there are some newer versions of it, but still sort of hundreds of kilobit per second or no megabit per second type things. So the way it kind of works is the following: there's a single wire over which serial transmission takes place, and there is an arbitration protocol through which nodes grab the bus, and then when they arbitrate for it. Each node, so it could be an ECU in your car. The ECUs are the little microcontrollers in the car, or nodes in the car. So the way it kind of works is that when a node wishes to transmit, it's a time-slotted kind of a protocol, and the nodes start sending out their priorities, and they send out the priorities in a serial order. So what they do is that they, in each time slot, they send out a 1 or a 0 depending upon what their priorities were. They start with the most significant bit, and kind of the idea is that after each time slot, they check whether what they transmitted matches what is actually on the bus. And the bus itself, what's happening is it's a single wire. Everyone is trying to work on it. So if someone pulls it down, in the sense that one of the nodes, let's say, have a 0. So let's take this guy as an example. First time slot, both the nodes transmitted a 1. Second time slot, both the nodes transmitted same value. Third, same value, but there's a discrepancy on the fourth one. In the fourth one, what is happening is that node B transmitted a 1, node A transmitted a 0. 0 overrides 1 because electrically there's a pull-up on that wire. So essentially what ends up happening is when they read back, they read a 0, and therefore node B stops, node B loses. So there is a arbitration that takes place every cycle, and at the end of the n bits of priority, only one person would remain standing, and then it gets to transmit. So it's a simple realization of a priority-based access scheme. That is, a bunch of nodes compete, one of them wins, and it gets to kind of transmit. The reason this thing has stood the test of time is just because car industry had no particular reason to change for the longest while, because information technology penetration was relatively low. But in recent years, with a whole bunch of sophisticated sensors, high rate data, stuff like that kicking in, so that has led to this impetus towards newer standards. And I mentioned that how newer standard is in the works. And European cars have used instead of CAN bus, a different kind of protocol in recent years, particularly some of the German cars, which is something called time-triggered protocol. But again, it was meant at more at a lower performance end. So we are seeing kind of with self-driving cars and all, kind of this industry being moved as well. But CAN bus you will find in a lot of microcontrollers. On the wireless side, there are a few things which kind of stick out as having played an important role in the embedded industry. So first is what is called as IEEE 802.15.4, or often and something built on top of it called Zigbee, and something built on top of that called IPv6 low PAN. Okay, so these are different organizations that have created a set of standards. It started out for work with sensor networks and home automation. One of the key things that they were driving towards was that the standard should be such that it maximizes opportunity for radios to sleep. That that the physical layer should be such that radios consume low power when they are not transmitting, back to our energy proportionality arguments. And finally, radios should be such that they can very rapidly wake up. So all of that kind of went into this thing, and since then there are newer versions of 15.4 that have emerged. The latest one uses something called ultra-wideband radios, which also have the property that they can measure distances and time very accurately, and so that's kind of a more recent enhancements to it. So This is used quite a bit. You will find it in particularly in the smart lighting industry as well as smart meter industry. So smart meters, which are talking to appliances at homes and all, the dominant radio standard there is this one. There's another one called Z-Wave, which is very common in home automation, kind of competes with Zigbee.
So Zigbee and 802.15 are the same thing.
Okay, so no. So 802.15.4 is the physical layer and the medium access control protocol. Zigbee is routing on top of it, okay, and a few other things. And then IPv6 LoWPAN is rest of the network stack on top of it. Okay, so they kind of just build up. So 15.4, strictly speaking, is just a reference to the physical layer and the medium access control protocol. Z-Wave is from a company whose name's just me, but it kind of became a sort of a de facto standard and is still there in the market in a pretty reasonably dominant way. So the difference is that even now when you go out and buy like security sensors or lighting switches and stuff like that, you would see that Z-Wave probably has a bigger market than 15.4, even though in smart lighting like LED bulbs and all, 15.4 is the one that dominates. So this will probably phase out over time, and it's closed source in the sense that you have to be a licensee and all, but there are software stacks for it, so you can run it on Linux or a whole bunch of other devices. So it has, lots of products and kind of a brain dead, almost very simple, very usable. Whereas Zigbee had a lot of usability problems and all. So this is still there, but my guess is over time, as they get the act together out there, it will penetrate. And then Bluetooth. So Bluetooth obviously started out with what is called as a classical Bluetooth, which basically mimics a serial port on a wireless thing in one of the profiles, and that's how sensors and microphones and headphones and all kind of ended up being around it. Over the past few years, one thing which has emerged around it is something called Bluetooth LE, or low energy, or smart. There are many different names for it, but the main thing is that Bluetooth LE is optimized for very low rate very kind of data scenario where again like a sensor sending a heartbeat, so it's like once every few seconds or once every second, those kind of low rate, small amounts of data at a relatively low rate, again aiming for radios which are much lower power than classical Bluetooth. Classical Bluetooth radios were in tens of milliwatts, and now you're talking about radios which are sub-milliwatt kind of thing. And that Bluetooth LE itself was a reaction to, again, another commercial standard, something called ANT. So for the longest while in the medical industry, sensors or typical like chest belts and all you will find with for fitness purposes and all, they were using ANT. Many of them still do. And Bluetooth LE, so the low power version of Bluetooth, basically took over that. And the big advantage Bluetooth LE has is that it's on your phones. So there was a while that many of the phones actually also had ANTs, particularly some of the Sony phones, for example, and the chips that companies like Broadcom were making, they had ANT support out, and actually iPhones also had ANT for a while, but at this stage Bluetooth LE has kind of taken over that, and that's the market with very low rate, kind of order of hertz type sample rates, and you're sending very small amounts of data like temperature reading or a heart rate reading or those kind of things. On the industrial side, there's something called wireless HART, which is kind of, you can say, is competing with 15.4 or Zigbee, except that what this HART tries to achieve is really rigid real-time control. You being able to guarantee delays between two nodes which are multiple hops away and things like that. So it's used in industrial automation, refineries, those kind of things, and also this is another standard which is HART was original one, and wireless HART was a wireless one. So at this stage, I guess in terms of the standards, then the players are the first one, 15.4 Zigbee and IPv6 low PAN, which I have not written out there. That suite of things, Bluetooth, particularly Bluetooth LE or Bluetooth Smart, and then on the industrial side, wireless HART. Okay, and Z-Wave, while they're still around, are probably at some stage going to disappear just because they are single company driven kind of things. Then when it comes to kind of a parallel competition to this, if you may, has come from A2.11. And A2.11 for the longest while has tried to penetrate into the embedded market. The big problem with A2.11 has been that its sleeping modes are not very efficient. Okay, so it intrinsically ends up, since it's optimized for high data rate and all, so when it comes to low power type operation, it has significant disadvantages in terms of ability to shut the radio down. The wake up times are very long, things like that. Its intrinsic efficiency in the active mode is not that great. But having said that, for many applications, this works out fine. So you will find it quite a bit in the embedded market, and even for things like smart light switches, things like that, you often see bi-side being used. Having said that, some of these things, Bluetooth LE or 15.4 in some modes and all, they are in microwatt type operating ranges. This is a far cry from hitting that. So unless your data rate requirements are high and all, this is for low power stuff, it's not the option. And then finally, many embedded systems do need to talk longer distances, longer ranges, and then of course there's a usual set of culprits in terms of things. Probably the more interesting one, which I have not listed out here, is the LTE Direct, which I had mentioned in slide earlier on. But LTE Direct is kind of the same LTE which we use on our phone, but for peer-to-peer mode. So two phones directly talking to each other without engaging a cellular-based tower, and it being able to exchange data. So that's certainly emerging. One other thing you would see is that just like using the same cellular infrastructure, there's a whole industry out there of what is called as M2M networking.
What sort of hardware do you need to implement LTE? Is there a specific chip?
Qualcomm chips.
Okay, so just anything Qualcomm you want.
Qualcomm chips that support LTE.
Okay.
But it's a standard, so I'm assuming that other vendors would also sort of be coming out with it. So when it comes to wide area type of things, the problem that you face is the following. So when we sort of deal with data plans and stuff like that, is one device, a data plan, there's a provisioning cost, stuff like that. But the embedded industry is very different. So imagine you're a company, you are deploying some sort of a product which needs to transmit data back using the cellular infrastructure. You're going to have thousands and millions of these devices. You're not going to be dealing on a per connection basis with these things. So the way that industry works is they do bulk purchases, and then the devices are going to be sending a few bytes a day. I mean, imagine something like a vending machine sitting in a remote location, talking back or connecting back. So those kind of markets. So there is a separate industry of companies which operate these M2M networks by basically buying data from regular carriers in bulk and then kind of dealing with companies which are seeking to deploy these kind of embedded devices. Even companies like Qualcomm and all often directly deal with it. Many a times they use very low end or older version of their cellular chips and all. Of course, higher power when you are dealing with longer distances, but there's a very rich market and there's a set of services and all these companies provide. How do you maintain things, location services, things like that, which kind of exist. So you will see these kind of things quite common. For example, like home security market, quite common now that the home security gateways, cellular, medical devices, Qualcomm pushes that quite a bit. Vending machines I gave as an example, also like those screens that you see in taxis and all now. Okay, so these are all examples of sort of custom embedded devices that have been created, and they kind of deal with these companies specializing in M2M. Medical industry is a big user of things like that. Okay, so yeah, I think I've already sort of made most of the points out here. So when it comes to sort of short range type radio choices, which is the likely scenario that at least a typical project in a course like this ends up facing, your choices basically are kind of the Zigbee 15.4, Zigbee 6LoWPAN kind of suite of things, or perhaps the Bluetooth end of things. These are probably the two most common ones. And it turns out that those microcontrollers I was mentioning and all, there are many of them which come with these things built in. So like you can buy microcontrollers from Atmel, Texas Instruments, which have a complete stack. So they have a 15.4 radio, they have a Zigbee stack, they have a 6LoWPAN stack. They kind of sell the whole package to you. So you're good to go. And likewise on Bluetooth side of things also, like TI really cheaply, like as in sub $10, you can buy little evaluation boards from them with sensors and all, which have complete radio stack and all on it. So very easy to sort of get into that game. Atmel, same story. They all have these kind of examples. So, the other I think other interesting thing which happened in the Bluetooth side in particular was the following. iPhone, Apple, when it first came out, it had Bluetooth obviously, but classical Bluetooth. But to be able to interface to iPhones using classical Bluetooth, you needed to put Apple certified crypto chip on your devices. So essentially, you needed to be an Apple licensee, which pretty much meant if you were just a sort of startup or a academic researcher or a hobbyist, you really didn't have any option, because going through that certification was extremely money intensive and all. You could, even if you attempted to buy the chips from a vendor like DigiKey or Avnet and all, they will first ask for the certification. So that path was out. There were some ways to circumvent around it by jailbreaking your phone and all. But with Bluetooth LE, or smart Bluetooth, that changed. So you can hook up any smart Bluetooth LE, Bluetooth smart type device to your to the iPhones also. Android never had that issue, but on the iPhone side it was. But given its market size, that had a huge influence. So, so the moment Bluetooth LE came into being as a completely open interface, you don't need any special licensing and all. It sort of really blossomed things quite a bit. In particular, Bluetooth LE has also become a great way for a lot of locationing services. So there is something that, again, Apple started, but there are Android counterparts, this thing called iBeacons. So iBeacons are really sort of low power beacons which basically send out, the little devices which send out Bluetooth LE beacon packet, okay, and with a unique ID, UUID on it, and they are being used in shops and stuff like that as kind of a proximity or location detector. So like in Apple stores, if you are near the table displaying, I don't know, Apple Watch, then it knows that you are close to it, and then you can kind of they can push stuff at you. You can have a different user experience. Museums are using it. My suspicion is, I might be wrong, that some of these services like Uber and all are also using it at airports and all to localize you much more closely, because they're able to see indoor positions very nicely now, even though GPS isn't there. So some combination of Wi-Fi based locationing and Bluetooth based locationing. So Bluetooth LE has been a bit of a game changer in terms of the kind of sensing devices that have emerged for phones plenty on that. Okay, the next one, power subsystem, very underappreciated but extremely critical in embedded devices. So your options, of course, when it comes to power supply, one is of course design things so that they are plugged in, but that's usually not an option for a lot of these things. So that leads to a whole bunch of other possibilities, battery being the most common one, either fixed battery as in non-rechargeable kind of stuff or rechargeable battery. But there are other interesting ones, is the whole concept of energy harvesting. And in recent time, we have seen the emergence of what is called as wireless power delivery. So you can deliver power remotely to a device, either via magnetic coupling or resonant magnetic coupling or using electric fields. So there are several companies in that direction, as well as by a combination of scavenging wireless energy from radio waves which are already around us, together with making your electronics very low power to have battery-less devices. I think I had mentioned that in the very first lecture, but there is we are seeing sensors and all at the stage which truly can just operate totally wirelessly, and they basically without any batteries, and they basically get their energy from Wi-Fi signals or TV signals which are just around in urban areas. Common to all of these is some sort of a power system in which you need to take energy coming from wherever and convert it into a form which is nice and clean for system for rest of the system to use. Now, one of the students had pointed out that in a slide early on in this lecture, I had a phrase called brownout detection. Anyone knows what is brownout detection besides you?
Is that when you momentarily lose power for a split second, you need to be able to account for that?
Not quite, no. I think you are referring in terms of the way we see it in the AC grid. So I guess in that sense you are right, but in the embedded system, not quite, yeah.
When the voltage dipped below the threshold needed to run properly.
Yeah, so when your battery has, so what happens is the following. There are many systems where we don't use regulators. And the reason we don't use regulators is because regulators themselves have an efficiency that which can be pretty bad. You may lose a significant percentage of incoming energy as heat in these regulators. So many low-end systems are often operated straight off the battery. The problem is when the battery voltage varies, and the thing is when it has sufficiently dipped, then your circuit can start misbehaving in pretty bad ways, can corrupt your flash, all sort of bad things can happen. So some of these microcontrollers you would see have these so-called brownout detection pins, and kind of the idea is that you basically want to go into a safe mode when things are misbehaving, okay? Otherwise you will see corruption of flash and things like that. So that's, yeah, so kind of related but not exactly. Okay, so but in general though, you would need a regulator just to keep the voltage under tight control. Noise should not creep in onto the voltage signals, onto the voltage, because otherwise bad things will happen to the hardware. Generically speaking then, your power supply system would have some source of power, a harvester, a grid, a charger, things like that, some source of storage. You may be continually connected to a power supply or only sporadically. So it could be like a cell phone where you only charge when you're plugged in, or okay, so some sort of storage. One of the innovations here in recent times has been that the movement potentially away from batteries to supercapacitors, which are highly dense capacitors. In fact, some of the very cool work in this space is happening right here at UCLA in chemistry department, where they're using carbon nanotubes and structures around that to store very high amounts of charge in a small volume. So the dream is that at some stage perhaps capacitors can approach battery-like energy density. What's the advantage of capacitors? Those are your E's.
They charge very quickly.
They charge very quickly. Okay, what else?
Perhaps they could get more current output.
Okay, so they can dump out a lot of charge in a short time. So that's why we use them in flash and all. What else? They're non-chemical, so safe for the better for the environment. Batteries have limited lifetime in terms of how many times you can recharge them. Capacitors have a lot more. So there are plenty of advantages, okay? And but the big negative they have is that their energy capacity is not that great. The energy that can be stored in a given volume, and that's where batteries excel because they are chemical. But there is a big movement towards that. So there's a lot of interesting stuff happening also in batteries. The other thing is a so-called thin film batteries. So these are batteries which are made, lithium batteries and all, which are made on top of a silicon or some sort of a plastic substrate, and so they're thin film as opposed to kind of these bulk batteries. And for wearable type devices and all, that's an attractive option. You would have some sort of hardware or software which would manage this process of when should the charge go into storage, when should I supply energy out of storage as opposed to directly from the power supply, all these kind of issues. And we see them actually in very elaborate forms on our smartphones, okay? So like oftentimes, or when you are plugged in and your phone is still doing some work, like, I don't know, background refreshes and stuff like that, should the charge go through the storage? Should I always operate on the battery? Should I go from the charger? One of the issues also comes up is that there are chargers which come in wide variety. So like even on our phones, the USB chargers, some of them are half an amp, some of them are 1 amp, some of them are as high as 2 plus amps. So your charger, even when you are connected to the supply, your charging power may be different, and also users charge at different times. So there are all sort of complicated things. If you have a other type of harvester like solar or some vibration based and all, then there is a lot more unpredictability when the energy is going to be there. So depending upon the system, sort of the intelligence that you need out here can be tremendously complicated. And then finally, all of this, whatever charge you're taking, then has to go through what is called as a DC to DC regulator, which is basically taking a DC voltage and then creating a stable DC voltage for the output side. And there's a potential loss of efficiency out there, which could be wasted energy. So a lot of work on creating extremely efficient regulators in recent years as well. An interesting, not quite related to this, but just wanted to bring out the importance of the whole power supply thing. So one of the things that when it comes to supplying power to computers in racks and data centers and all, so Google ran a competition in over the past couple of years with some humongous multi-million-dollar type prize on creating power supplies which were extremely efficient. And recently it was won by some Belgian company, okay, who basically really pushed the envelope quite a bit, okay. And thing is, I mean, any saving in efficiency, any improvement in efficiency multiplied by millions and millions of servers and all just kind of translates that. Same story kind of out here. Lots of work went into improving efficiency of the regulators in recent years, quite a bit. So big area of activity in recent times, particularly, like I said, on the harvesting side. And some pretty interesting harvesting modalities are needed in many cases, like implantables, as you might imagine. It's very difficult to recharge them, so lots of interesting ideas floating around there. I'm going to skip the next couple of slides and okay, maybe not. So when it comes to regulators, one thing that you would see is kind of the circuits that do this regulation fall into two very broad categories. One are those which basically use some sort of an amplifier. Conceptually not all that different from amplifiers that you use in, let's say, your audio system and things like that. And kind of the idea is there's some sort of feedback control so that the output voltage is maintained at some sort of a desired value. And these things are called linear regulators. They tend to be not very efficient. So the kind of power supplies that you are instead going to find, so the efficiency is here, like for example, in this case, 60% efficiency. So you're losing a big part in as wasted heat. So the power supply that you would find quite a bit more commonly are what are called as switch mode power supplies. And very conceptually, the way they work is the following: that there is a switch, and when you close it, charge flows. When you open it, charge doesn't. And by controlling the rate at which you are, the duty cycle with which you are controlling the switch, so every time period, you keep it on for some fraction of time, keep it off for some fraction of time. So you control how much charge you are dumping onto the capacitor on the output side, and therefore the voltage. So the way these things work is there would be some sort of a period, usually tens of kilohertz, and then within each cycle, some fraction of the time the switch is closed, the remaining fraction is open. So these are called switching regulators. They lead to much more efficient type power supplies, and very commonly kind of used. The negative out here though is that the switch, which is rapidly closing, itself injects noise, and so one therefore has to kind of control that. But this leads to smaller supplies, much more efficient supplies, and you are going to find those. Okay, so much higher efficiencies. Okay, so switch mode power supplies basically are efficient but have these issues. Okay, when it comes to storage, I think I've already discussed some of these issues, but very broadly we use storage for two purposes. One is systems that are designed to operate untethered, far away from a grid. So we need some sort of thing there, long-term storage, and that's primarily batteries. And then there are cases where we need to cope with intermittent power supply, like a solar cell or something like that, in which case batteries and capacitors also. And oftentimes we now see batteries and capacitors used together. So some of the phones, some of the structures I've seen where they may have a capacitor which is first charged, so that your phone is your device is quickly charged to have some operating energy, and then the battery is kind of the backup. Some of the newer Android devices you would see they are being advertised with a rapid charging capability. So like Samsung's phones and all, they advertise that how they have a very quick charging thing. Anyone knows what's going on there? Like, what's the magic? So this is a technology that sort of Qualcomm pushed, but basically what they do is they kind of charge, that they're playing with the current they supply during the charging mode of the battery. So they kind of overdrive, so to say, during the charging mode. Comes at some cost in terms of the lifetime of the battery, but the advantage is that you are able to get a quick charge very rapidly. So two issues around batteries, at least in mobile devices and wearable devices, that we face is, number one, we want a long lifetime, and the second one is we want quick charging. Okay, because and both of them are being kind of addressed by these kind of games on how we manage kind of the overall system. There's no fundamental improvement in batteries themselves which are currently causing these things, although at some point in time that might happen, but we are already at lithium ion. There isn't a whole lot of other things left in the periodic table to sort of play with, short of become explosively dangerous, basically. So there are other type of technologies people have talked about quite a bit when it comes to batteries. So things like storing things as hydrogen in some sort of a material structure out there. Fuel cells, many of you may have heard of that term. So I still have a Scientific American issue from late 90s talking about how fuel cells in smartphones were just 2 or 3 years away, and it never happened. And most of the reason is, again, a lot of these technologies, packing a lot of energy in a small volume comes with a lot of risks and dangers and stuff like that. So that's the challenge that has held things back. Lots of options, but a slowly moving technologies, and perhaps the most attractive thing here is going to be the role capacitors are going to play. So I think I'm running out of time for today's lecture without diving into a new one. So let me defer this thing to Thursday, where I'm going to do a quick view of what the technology options are when it comes to some of the storage technologies. So again, try to connect with me so that I can start sort of discussing project.
Well,